Hello, I'm Peter Van Horn presenting the Automatic Mobile Dry Food Treat Dispenser. The purpose of this project is to provide an alternative method for feeding household pets who prefer grazing from the floor to eating from their bowl. This system scatters food in a controlled fashion for consumption by the pet. It can be either manually or automatically operated. The objective of this project is to produce a mobile system which dispenses pet food. This is accomplished using a robot that is a self-propelled unit, has an easily accessible food hopper, dispenses small amounts of food periodically, and can be either manually or automatically controlled. The robot is remotely operated using a separate controller which switches between manual and automatic control. While in manual control, the controller directs movement of the robot as well as dispenser operation. In either mode, an LCD reports instructions the robot is carrying out. The microcontroller platforms used in this project are one Arduino-compatible Mega 2560 Revision 3 board and one Arduino-compatible Atmega 328P Nano board. These were programmed using the Arduino Integrated Development Environment version 1.8.12 from a Windows 10 desktop PC. Peripheral components used include two HC05 Bluetooth modules, one HC-SR04 ultrasonic sensor, one joystick module, three MG995 servos modified for 360-degree operation, and one push button. The power supplies used in this project consist of two 9-volt alkaline batteries and one 11.2-volt lithium polymer battery. The alkaline batteries are connected using I-type snap connectors, and the lithium polymer battery uses Dean's T-plug connectors. A lithium polymer battery tester with low voltage alarm is used to avoid battery damage, and a DC-DC converter is used to step down voltage for use by the servos. Two 400-point breadboards provide power rails and allow jumper wires to connect to the nano board. Jumper wires are used to connect all peripherals to power and the microcontrollers. Additional materials used to construct the robot and its controllers include picture-hanging adhesive strips, cardboard and paperboard products including a small shipping box for the controller housing, oatmeal containers for the shell of the robot, and a potato crisp can for the hopper. Other items are craft sticks and toothpicks, hook and loop fasteners, nuts and bolts, hot glue, electrical solder, and solder seal wire connectors. Now for the physical assembly of the system, beginning with the robot. The chassis of the robot was constructed using scrap corrugated paperboard with the intention of using an oatmeal can for the shell. The Mega 2560 board, powered by a 9-volt battery, provides the robot's microcontroller. The automatic drive's object avoidance feature uses a forward-looking ultrasonic sensor. Solderless breadboard power rails provide the buswork for all peripheral components. The top rail supplies the servos exclusively, while the bottom rail supplies the ultrasonic sensor and Bluetooth module. Propulsion is provided using two servos, and the food dispenser is operated by the third servo. Servo power is provided by the lithium polymer battery. As this battery has a low voltage limit of 3 volts per cell or 9 volts across the battery, an alarm is used to aid in avoiding battery damage. Mounted on the front of the robot is the Bluetooth module and the DC-DC converter that takes input from the lithium polymer battery and outputs the 5 volts and relatively high current capacity needed by the servos. The transmitter and receiver of the ultrasonic sensor also pass through the chassis structure. The dispenser mechanism was constructed using corrugated paperboard, craft sticks, toothpicks, and hot glue. The interface between the dispenser and the servo is made from floral wire, a plastic sheet, and is held in place using dental floss. A shaped craft stick is hot glued to the servo horn. As the servo is operated, its attached craft stick is grabbed by the floral wire hooks, turning the dispenser mechanism. The dispenser uses a potato crisp can as its hopper. Each component of the dispenser is secured in place using dental floss. This allows easy disassembly as needed. The final component is the access cover. With food or treats added to the hopper and the hopper's cover installed, the robot is ready for operation. Now we turn to the assembly of the controller, which provides the operator with an interface to direct the robot using a joystick with integrated push button in manual mode and a mode selector switch to toggle between manual and automatic modes. The LCD screen displays the instructions being carried out by the robot. The LCD is hot glued in place while the push button is pressed through the corrugated paperboard with leads soldered and then glued in place. Also attached to the cover is the Bluetooth module set as the master device and paired exclusively with that of the robot. A breadboard power rail provides the buswork for the controller, which is powered by a 9-volt alkaline battery. The joystick is mounted on a raised platform of stacked cardboard. A breadboard without power rails provides solderless connections to the Nano microcontroller board as well as the potentiometer for controlling LCD brightness. Having completed discussing the construction of the controller, let's take a look at the program that makes it work. The controller program includes the Arduino libraries Liquid Crystal for the LCD and Software Serial, which allows digital input-output pins to be used as a universal asynchronous receiver-transmitter port. This frees the Nano's single hardware UART port for troubleshooting. As a comment in the code, the wiring table for the Nano is included for convenience. The first variables defined are for the interrupt-driven mode toggle feature. Using Software Serial, the Bluetooth module, designated BT Master, is assigned digital input-output pins. The joystick is assigned one digital pin for the integrated push button and two analog pins, one for each of the axes. Robot report variables and character arrays are initialized, and using the Liquid Crystal library, the LCD pins are assigned, and a wiring table is included for convenience. Custom LCD characters are defined that are used to indicate propulsion servo operation. In the setup function, the joystick push-button variable is defined as an input and along with the mode variable is set to high. The mode pin is defined as an interrupt that triggers when the mode pin falls from high to low. Serial refers to the Nano's hardware UART port, which was used exclusively for monitoring and troubleshooting. BT Master is initialized at 9600 baud. LCD is initialized for 2 rows of 16 characters each, and the custom characters previously defined are created. In the loop function, if the controller reads a message beginning with the letter R, the follow-on comma-separated characters are parsed into variables to be used for display on the LCD. Motor order data is converted from degrees into index positions for the custom characters. The first row of the LCD is populated with data labels mode, food, and distance, each separated by a custom character. The second row displays the current mode, auto or manual, indicates if food is being dropped, and shows the range detected by the ultrasonic sensor, again separated by the custom character. The character array order is populated with comma-separated values from mode and joystick inputs, the first character being the letter C. This data is then transmitted using BT Master. The final operation in the loop function is a 50 millisecond delay. The controller code is concluded with the mode interrupt service routine. When the interrupt is called by pressing the mode button, the mode variable switches states from high to low or vice versa. The final piece of the system is the robot program. Using the included Arduino servo library, each servo is defined: dispenser, left motor, and right motor. Dispenser and drive motor variables are initialized. Mode, ultrasonic sensor, and automatic mode variables as well as the report character array are initialized. Within the setup function, the servos are each attached to a microcontroller pin. Again, serial refers to the hardware UART port. The Mega 2560 microcontroller has 4 such ports, and serial 1, used for the Bluetooth module, is initialized at 9600 baud. Joystick button variable associated with the dispenser is defined as an input and set to high. Ultrasonic sensor pins are also defined. Completing the setup function is the random number generator initialization. Arduino's pseudo-random number generator will generate the exact sequence of random numbers for a given random seed value. By setting the random seed function to read the unconnected analog 0 pin, the static red will result in a different sequence of random values for each run. The first operation in the loop function is to parse instructions from the controller. The ultrasonic sensor is then operated. If the robot is in manual mode, auto mode variables are reset. Operating the joystick push button sets the dispenser servo operation counter, and the joystick's 10-bit position data is converted into degrees for use by the drive servos. The position of each drive motor is then calculated using the X and Y axis data from the joystick. In automatic mode, the dispenser counter is decremented until reaching 0. The counter is then randomly set, and the dispenser is operated. The automatic drive direction is determined first by the ultrasonic sensor reading. If an object is closer than 44 inches, the robot will operate both drive motors to evade left until no objects are close. 44 inches was selected based on the 15-degree detection angle of the sensor and the 11.5-inch width of the robot. With no object within the minimum range, the robot travels in the previously determined direction until the drive counter reaches 0. The counter is randomly reset and a new direction influenced by the last one is randomly selected. The randomly determined direction is then converted into degrees for use by the servos. While the dispenser operation counter is not 0, the dispenser servo position is set to 5 degrees, otherwise it is set to 0. This is a departure from the normal continuous operation servo, as the zero movement angle is normally 90 degrees. Each servo motor receives its position order and the report character array is populated and transmitted. Finally, a 50 millisecond delay is executed. Now, let's see the system in action.
Alright, go for it. Alright, and then drive it back to the garage door. Alright, and then push the yellow button. Alright, and then push the yellow button. Alright, and press the yellow button.
Frenzy, Frenzy. Frenzy.
You can let the dog go.
Let me know when to stop. There it goes. See if he notices it. It dropped nuggets. Go get him. There we go.
The objectives of this project were to produce a system that dispenses pet food using a self-propelled robot that dispenses small amounts of food either manually or automatically, and a controller that can remotely switch between automatic and manual modes, direct movement and dispensing of food, and report actions being taken by the robot. These objectives have been met, and the system provides a successful alternative to the food bowl, so long as the food lasts. This concludes the presentation of the automatic mobile dry food treat dispenser. Thank you for watching.